Alright, silly people, here's the situation. We have a potential that is a particle, it's an infinite square well, but there's a delta function potential in the middle. Uh, like, and I drew a little cartoon of it here, and labeled regions 1 and 2, and we're going to solve the Schrodinger equation for region 1, and then do some other stuff with even and odd wave functions to get the energy eigenvalues for the system. So, um, the Schrodinger equation in region 1, this isn't anything that we haven't seen before. It's this, and then it's a second derivative of the wave function in that region equals e psi 1, and then you can collect all of the terms on the right into a constant k squared psi 1, where k is just defined as being root 2me over h bar, and then this has the solution of a sine kx plus b cosine kx, whether or not we have an even or odd wave function. That's what psi 1 is. But now we're going to start talking about the odd wave function first, because I think it's a little bit simpler. So for odd wave function, we have the constraint that psi of x has to, or psi of minus x has to be equal to minus psi of x. That's what odd functions are. So to do that, we'll have that psi 1 is the same as it was before, and then to have the parity thing, cosine is an even function and a is already, or sine is already odd, so we just have to change the sign of the cosine function, and you get something like that. We can look at boundary conditions to figure out what b is in terms of a. We'll try psi of 0, so the fact that the wave functions have to be continuous at the boundary, and this just gives us b on the left side and minus b on the right side, and that's going to tell you that b equals 0, right? So in fact, both psi 1 and psi 2 looks like are a sine kx, so we don't really need b in terms of a anymore. We can do the boundary condition of psi of a equals 0, so because the wave function in the region outside is 0. So this is going to be a sine ka equals 0. And then you cancel a out and you find that ka equals n pi for those solutions, and then you can expand k out like this. This is going to be over h bar, and then you can use this to solve for e as being n squared pi squared h bar squared over 2ma squared, which is the same as the infinite square well energy eigenvalues, right? Nothing's changed there, and that's because that for odd wave functions, the wave function is always 0 at x equals 0 anyway, so the delta function potential doesn't even really come into play for the odd wave function, which is why we get a situation where it hasn't really changed. So the even wave functions are a little bit more involved, and the constraint on those is that psi of minus x has to equal psi of x. So we're finding that psi 1 is the same right? It's still a sine kx plus b cosine kx. But then to get this even behavior, we have to switch the sign on the sine function because sine is odd. We get that sort of thing. We can try to get a relationship between a and b by doing this boundary condition again. So the continuous, the fact that they're continuous, but this is just going to give you b equals b, and that's not exciting. So we have to go a step further and use the fact that the wave function is smoothly varying, or that it's not smoothly varying, that it has a weird sort of peak of the derivative. It's equal to minus 2m alpha over h bar squared psi 0, right? So for that, we're just going to use, this is going to be ka cosine of 0, which is 1, and then plus kb sine of 0, which is 0, so never mind about that one. And this is also going to be plus ka from that sine function, and that's equal to this junk over here. This is just going to be b. So we can add these up. That's just 2ka on the left side, so we'll cancel out 2's. So we just have minus m alpha over h bar squared b over here. So we can solve this for b and be like h bar squared k over m alpha a equals b. So now we can rewrite our wave functions. We're going to have a times sine kx minus h bar squared k over m alpha cosine kx, and psi 2 looks like minus a sine kx plus h bar squared k over m alpha cosine kx, right? So that's funky. Then to get the energy eigenvalues, we do this guy again, so psi of a equals 0. So let's just do this with sine ka, so the psi 1 is what I'm saying. So we'll do a sine ka minus h bar squared k over m alpha cosine ka equals 0. We'll let the a be canceled out, and we'll divide everything by cosine ka. So we have tangent ka minus h bar squared k over m alpha equals 0. And this is kind of a transcendental equation, so we're going to switch to a Desmos screen to figure out what the solution for Ka is. So this is the Desmos window. I wrote the equation again, except I just replaced I replaced k with x, so this is a plot of k, pretty much. I did the same thing here. And I replaced alpha with b, but it doesn't matter since I sent them all to 1. And we're just going to look at where it crosses the 0. So it crosses at 0, right? So that's fine. But then it also crosses over here, which is pretty much just pi over 2. Or that's actually pretty much 3 pi over 2 is where it's crossing there. And then over here it's crossing at 5 pi over 2. So it looks like it's crossing pretty much consistently with odd powers of pi over 2. So we're going to use that. Looks like Ka equals n pi over 2 for odd n. That's interesting. And then we can expand the definition of k. This is over h bar, and then this is n pi over 2. can solve for e, and you'll get n squared pi squared h bar squared over 8 ma squared for odd n, which is a bit different from the infinite square well, but yeah, nice.